So I wanted to talk about one of the successes of Diagrammatic Monte Carlo in addressing a long-standing physical problem of how an insulator develops in two-dimensional Hubbard model. And I'll start with thanking my collaborators. Part of the work was a PhD work of Feder, who is now in Paris. Part of the work was done by Aram, and recently we were joined by PhD student Connor, and a major part of the work was done in collaboration with James, Nikolai, Boris, and Eugene. So as a quick motivation, I just wanted to point out that current experiments in cold-particle atoms have reached quite non-trivial regimes of long-range correlations, and these are regimes which are actually quite challenging to address with current methods we have. But most interestingly, they've reached temperatures low enough to actually study the metal insulator physics, and it will be quite useful to actually address this problem in a controllable way so that they can actually go there and measure what is predicted. So the problem, the main ingredient, of course, of the Hubbard model with half filling is that the Fermi surface is nested, and there's a natural tendency towards antiferromagnetic instability. In particular, the ground state is always gapped for any non-zero value of U. However, there's a competing effect. Of course, the Riemann-Wagner theorem tells us that there's actually no long-range order. So the problem becomes, unless the temperature is zero, so the problem becomes quite non-trivial. And when the correlations, when the antiferromagnetism is suppressed, the problem has been studied very thoroughly. And pioneers actually of solving the problem are in this audience, and it's well understood that it's expected that the system will undergo a metal to insulator transition. However, in the pure to the Hubbard model, there's not so much actually where the antiferromagnetism is the main effect. Not so much has been done in a controlled way. Perhaps the most advanced work is this one done by Thomas and collaborators, where very advanced methods were used to actually demonstrate that the insulator appears in a crossover. And however, the study already demonstrated that the problem is very challenging because the correlation length was found to be very large across the crossover, and it's really difficult to obviously extract reliable results from finite size calculations. I mean, D-gamma A, of course, is an infinite size system method, although it uses meshes to deal with the K-space. But any finite size method like quantum Monte Carlo is probably going to be suffering quite a lot. So diagrammatic Monte Carlo, as we know very well, is precisely suitable for these kind of things because it works directly in the thermodynamic limit, where an observable is expressed as in one formulation, the Taylor expansion with respect to certain auxiliary expansion parameter, and the general setup that is used is this we have seen over these two years, is typically one with an effective action where we introduce some arbitrary field in our effective actions, add and subtract, treat part of it in the Green's function. Well, it can serve different purposes, as we've seen in yesterday. It could improve convergence of the series, or in fact today in Christian's talk, it greatly helps. But we're using it mainly for improving the Monte Carlo efficiency. But then the observables, correlation functions in particular, would be given by Taylor expansion of this auxiliary expansion parameter. And computing the coefficients, well, at least in the parameter regime of relevance to this problem, is most efficiently done by a family of determinantal diagrammatic methods. Well, the idea that Ricardo suggested, which builds on earlier work, where it was realized that a determinant built on Green's functions sums all possible diagrammatic topologies, was used very successfully to compute the partition function and, well, simulate sample the partition function, simulate the statistics for the partition function, and was realized by Ricardo that in fact you can subtract all the disconnected diagrams out of a factorial number of diagrams, which you can compute very cheaply with only n-cubed operations. You can subtract all the disconnected ones in just an exponential number of steps. Naively, one would expect that to be factorial. That's only exponential. And in fact, as Fedor pointed out to me, at some point you can actually do it using fast subset convolutions in n squared 2 to the n. But actually, the leading cost, typically, if you do it straightforwardly, leading cost of this subtraction is computing all the sub determinants, all the principal minors of the determinant, of the main determinant that you're actually subtracting here, and that scales as n cubed 2 to the n. However, in his PhD work, Fedor came up with a nice way of improving this, and that's not a bottleneck anymore. It's just a order 2 to the n. That was actually a very important improvement for us, which allowed us to go to slightly higher orders and improve our accuracy. Now, and as I'll show, this works very well for correlation functions, but we also want to be able to compute self-energies. And, well, it's quite natural to extend this idea by subtracting all irreducible diagrams. It just can be done similar in a similar number of steps, just slightly higher times n squared. And there are different technical implementations. The Paris group has done a similar thing. We have this algorithm that works in the momentum space, which we find convenient for certain problems. So, however, this is indeed an efficient way of computing the coefficients of the series. But once you've computed them, and you can go to quite high orders. Well, here I'm showing the results for up to 10th order. This is imaginary self-energy as a function of inverse diagram order. You see that even though you know all the coefficients, of course, the answer does not make any sense because the series diverges, and we come to what was discussed at length yesterday, how to actually extract a physical answer out of knowing these coefficients once we're able to compute them with decent accuracy to really high order. The approach that we take is, well, we start by locating the singularity on the complex plane by just looking at the simple ratio test. We can find it roughly like this, and well, and for this particular data, it's -5. We don't need it to know the location of singularity too accurately, because what we do first is that we apply a conformal map. I don't need to go into details. It was discussed at length by Xavier, but I just want to mention that typically the singularity on the negative real axis, it's expected to correspond to the superfluid transition. So the type of the singularity is not a simple pole. Typically, it's some kind of branch cut along the real axis, and we use a map that maps this branch cut onto the unit circle, so that the physical parameter, the expansion parameter psi, which is 1, when we want to evaluate the series, is within this unit circle. And indeed, if we use this particular map, we see that the series that we obtain actually does converge. However, it converges. I mean, first of all, we see that it's the second singularity. Again, we can run the ratio test on the transformed series. We see that the second singularity is at u around 9, which is higher than the one that we're evaluating at. This particular beta r for u7. So the series converges, but it does converge quite slowly. So we still need to extrapolate the series, and the way we do it is using this so-called integral approximant technique, which is, the idea is essentially to approximate the self-energy as a function of the expansion parameter by a function that has the same Taylor series up to the maximum order that we have, and solves this ordinary differential equation. So, and Q, P are polynomials of the corresponding orders, and is obviously constrained on the number of orders that you can have given a certain number of coefficients that you've computed for the series. This may look unfamiliar, but you're probably familiar with its special cases of this approximant technique. Well, the well-known Padé approximant technique is just a special case when this Q is 0, and the logarithmic derivative Padé approximant technique, which is slightly more powerful. It allows you to deal with algebraic singularities. This one is a special case when the right-hand side of the equation is 0. And by the way, this is all, of course, old school 1970s approaches, which proved quite very powerful, actually, for locating phase transitions and all sorts of analytic continuations in field theory. So, of course, the more general integral approximant technique has an advantage that it has quite a general structure of this approximant. Well, first of all, the singularities are found directly as zeros of this function q, so it's, there's no problem to find where the singularities are with an error bar if you want, of course. And close to the singularity, the form of the approximant is that of an algebraic singularity plus some regular part, and which is quite typical for a phase transition. So we expect it to be quite powerful in capturing the structure in capturing the asymptotics of our series, except, of course, in 2D we don't really know what the structure of the series, what the structure of the phase transition is, because the phase transition is a very quite a difficult analytic structure, typically Kosterley-Staudish type. But we see that there's no, as I'll show in a minute, there's no discrepancy from this approach beyond the error bars, which validates itself consistently. So if there was any discrepancy if we could resolve any difference from this general asymptotics of our answer, we would see that we would have to modify this approach further, but we see that within the error bars, there's no need for it. Right. So we can also do the same thing essentially in an automatic way without any conformal map. So you can just apply the integral approximant approach to the original series. And it will immediately give us the two singularities that we have discovered through the consecutive conformal maps with a certain error bar. And it has some noise, of course, and it will give us the approximate values of the powers of these singularities. Okay, so those are generally, of course, branch-cut singularities. And so it does give you a lot of information about the structure of the series automatically, and also it's a nice tool to control the accuracy because you know, what I need to do is I need to plot my answer as a function of different choices of those formally arbitrary M, L, and N. There are some reasons to expect some of them to be more adequate than others. But if you do it for different choices and observe that the answer does not depend on the choice, that gives you confidence that your error bar is under control and you've captured the analytic structure of the series. So actually I should say that a lot of work goes into actually seeing how this thing breaks down and trying different cases that you cook up and just to see how reliable that is. And indeed, we've seen that it works as we expected to.
Here you have counterterms, the original series.
It has just the basic counter term, which is a shift of the chemical potential, right? Just basically, yes, removes. Yes, just the chemical potential shift. Right. Okay. So and then of course we can repeat because now it's all automated. We can repeat this. For different momentum points of the self-energy quite straightforwardly and reconstruct, for instance, the momentum dependence of the self-energy. We can use that to find for instance, the momentum distribution in the system and see that, you know, for this particular regime of U7, temperature 0.2 and some 6% doping, it's quite different from the non-interacting system. And I should say that currently it's the best one can do for the self-energy. I don't think there's any method that can do it with arbitrary momentum resolution and in this particular regime. Right. Okay. So back to the metal to insulator crossover problem. Well, having access to the self-energy allows us to identify essentially quasi-particle properties from looking at the self-energy. We use the standard approach of well, we just look at the self-energy as a function of frequency, and if the self-energy bends up, it's the imaginary part of the self-energy. It's considered to be metallic, and an insulator corresponds to a pole developing at zero frequency. And so we see when it bends down, we call it a generally non-Fermi liquid. If it happens along the whole Fermi surface, we call it an insulator. And the crossover is essentially just, we define it as the location when the lowest, when the values of the self-energy at the lowest Mitsubishi frequencies change places. So when it goes from going up to going down, it changes, the difference changes sign. We call that crossover. So the result, it was flashed yesterday in Michel's talk, is, well, essentially, this is the diagram in the temperature in U plane, where we see that as, you know, we start low enough temperatures, we see good metallic behavior in the self-energy. As we increase the U or lower the temperature further, we see that the self-energy becomes gapped first at the antinodal point, and then as we keep lowering the temperature, increasing the U, the Fermi surface, the gap proliferates across the Fermi surface and eventually reaches the antinodal point here, beyond which the Fermi surface is fully gapped. So it's quite interesting that the metal to insulator crossover essentially completes within this kind of low U, what would normally be considered to be a low U range, up to about 4. So beyond 4, as one lowers the temperature, you enter essentially into the, you know, qualitatively Heisenberg physics without any ungapped excitations whenever you can define those. Right. So we can also look at well, something that is actually observable. I mean, the problem, of course, with the self-energy is that you cannot observe that in an experiment, but you can at least observe the momentum distribution, and we see that momentum distribution evolves across the crossover, where we start with something which is more resembling of the Fermi surface, but then as we cross over to the insulating regime, then here at the antinodal points, the momentum distribution is suppressed and it becomes more circular inside the insulating regime. We can also look at how the self-energy in the K-space in the Brillouin zone increases. Well, expectedly it starts with the antinodal points and then becomes bigger at the node eventually. But this one I think is quite interesting because here you see the difference between the two lowest Matsubara frequencies, and the blue shading corresponds to insulator-like behavior, and the red corresponds to metal-like behavior. And you see how increasing the U, the Fermi surface becomes gradually gapped everywhere. Right. So, however, it's important to keep in mind that our criterion for the metal to insulator is somewhat conservative, because it would be quite natural actually to expect that well, before we have this curve bending down, like this curve is already not exactly fermi-liquid. It does show non-fermi-liquid properties. So actually, it's interesting to look at the physical observables that one can actually go and measure, and there we see that. Oh, it's surprising why it became blurry. It was okay in my computer. Sorry for that. So it's a busy plot, but basically one point that I can make right away is that in physical observables, for instance, in compressibility, the crossover begins earlier, and the separation between scales between the metallic behavior and insulator behavior becomes even wider. So the system becomes non-fermi-liquid. Well, I should maybe make an aside that I have feeling, fermi-liquid is not the typical fermi-liquid. So when I say non-fermi-liquid, I don't mean the non-T-squared behavior, because it's not T-squared anyway. There's logarithmic corrections to everything. But in the sense that it has metallic quasi-particle properties. Right, so the system becomes non-metallic before the self-energy. So the self-energy data here are the ones I showed on the previous slide are the green points, and I'm going to guide you through this figure gradually. So let's start with double occupancy. So when one looks at double occupancy, yeah, oh yes. So it has an interesting, quite actually characteristic, as I'll argue, non-monotonic behavior, because as you lower the temperatures, double occupancy function of temperature, as you lower the temperature, it first goes down, and then it starts rising again, and then it goes down. So that corresponds to this cut, for example, and here the points by the arrows are actually these red points. The red points, they enclose an area where the derivative of double occupancy with respect to temperature is negative, and this has importance due to the Maxwell relation. Essentially here the derivative of entropy with respect to U is positive. So in fact here, if you're in this regime, as was noted by Felix and co-workers a long time ago, here if you increase interaction adiabatically, you will be cooling the system. It's a wide regime here. However, just on approach to the insulator regime, what happens is that the sign of derivative always of double occupancy always changes. So you always have a positive slope on approach to the insulator, and that corresponds to the development of the local magnetic moment before you can support the antiferromagnetic insulator state. Now, compressibility offers a more direct a means of observing insulating behavior. In particular, in a half-filled metal, the derivative of compressibility with respect to temperature is negative. In the insulating regime, it is clearly positive. So we see as these red points correspond to the points where the derivative changes sign. And we see that that happens quite early, but it's quite useful quite early compared to all the other processes that I'm going to mention. But it's quite useful to break down the compressibility into local and non-local contributions. It's just a sum. Well, it's related to the density correlations, and clearly it's just a sum of just a trace of this correlator. And we see that the net local contribution has a sign that is opposite to the non-local contribution. So actually, the net compressibility is a result of near cancellation of local and non-local fluctuations in density correlations, which is quite non-trivial. In fact, if we were to switch off all the non-local effects, then this crossover line in compressibility would be moved beyond the double occupancy crossover line. So the non-local in this regime of the non-Fermi liquid behavior, the non-local correlations are crucial, and we can look in more details of what they look like. I don't want to spend too much time on this, but we can see how the so-called correlation hole develops as we increase the interaction. Basically, well, a hole, as the name implies, just punches out some density around a particle due to interactions. Well, interestingly, the magnetic correlations are quite, when we look at the spin-spin correlation function and the correlation length, and the correlation length in the correlated regime is quite not so high when the crossover happens. It becomes of order 10 only below this blue line, and this is also quite natural for a correlated regime. In fact, as we if we consider the crossover at lower temperatures and lower U values, then the correlation length, magnetic correlation length at which the crossover happens becomes progressively longer and longer, corresponding to the physics becoming more and more mean field-like. Right. So the magnetic crossover is easier seen in the uniform spin susceptibility, which, well, generally deviates from the Curie's law below temperature 1, but it actually experiences a maximum, and then it's supposed to go down, but we don't have the accuracy to show nice data below this, but we can identify the maximum, and the maximum is given by this, the blue closed circles. We can also look at the destructive factor. I'm not going to go into details. It has some interesting effects, anisotropies, etc. And interestingly, we can see the signature of this non-Fermi liquid regime, which happens between the compressibility crossover and the magnetic crossover, where basically we can look at the derivative of the kinetic energy with respect to temperature, and see that it has a maximum where the maximum corresponds to the beginning of the non-Fermi liquid regime, somewhere around this line, and then it changes sign, as it should actually in its later insulator below the insulator line. The temperature derivative of the kinetic energy becomes negative, but by looking at the plot, we can identify which regime corresponds to a non-Fermi liquid. It's the one between the maximum. Well, clearly in the Fermi liquid, the derivative is positive, and it keeps growing, in fact, but it reaches a maximum just where we transition to the non-Fermi liquid. Right. So just to flash, I know I need to wrap up, but just to flash the slide, it's actually quite interesting that we can infer a lot of information about the nature of the physics by considering the nature of the physics of the system by considering the entropy curve. So if I plot a family of curves corresponding to different u values, I mean, obviously I immediately see regions where I have adiabatic cooling by increasing the u. So my entropy rises with u here, but then on approach to half filling, I see that there's a crossover and entropy starts going down as a function of goes up as I increase, goes down as I increase the u, right? So the behavior changes, and that corresponds, of course, to the fact that close to half filling we need to form the magnetic moment, and as I argued a few slides ago, this derivative corresponds to the contribution to the magnetic to the local magnetic moment. Also, the appearance of the inflection point at high u's signals that the change of the derivative in compressibility happens, which also gives us an indication that the system transitions from being metal-like on the left of this line to insulator-like on the right of this line. All right, so with this, I'm going to leave my final slide, and thank you for your attention.